Okay, well, hello everybody, and welcome to the TVS Science Colloquium. Today we're going to hear a talk from Hanno Marais of the South African Astronomical Observatory, and we're talking about the rapid classification of transients and the integration with the South African telescope facilities. So, look forward to it. Hanno, take it away.
Yes, hi everybody. So my PhD project, the title doesn't really say it all, but it's fast classification and anomaly detection for the LSST. And specifically, I'm trying to figure out how fast we can theoretically predict what class a transient that we've never seen before we can classify that. And for that, I have been simulating the plastic data, which was a challenge on Kaggle, and specifically using their regional models to re-simulate a few thousand light curves so that we can work with the new cadences from LSST. And just a quick outline of this project, I'm going to start with a little short evolution of astronomical data, just to show why it is necessary to do these machine learning processes to classify new transients, and then go over one or two machine learning classifiers that I considered to use, and then one slide on the Rubin LSST. I will then go over all the simulations that I did and artificial neural network that I chose, and then used to build my classifier and anomaly detection framework with. So the evolution of astronomical data through time, as we can see here, during the centuries, the amount of data that we get from our telescopes has increased dramatically. And when we plot this, we can see that there is a logarithmic scale to the amount of data that we get, starting from Galileo's first observations of hand-drawn images of Jupiter and its moons, all the way to what we have today of our large simulations of survey telescopes.
Hanno, sorry to interrupt.
Yes.
We are seeing a big gray square on the right-hand side of your slide. I think maybe you have one of the Zoom windows overlapping the display.
Let's check.
Ah, that's better. Thank you. Right, let's come back.
Come back now?
Yeah.
Yeah, and why we're showing that. Right. And also as our telescopes have increased in size and there is increased in resolution, our time coverage and wavelength coverage has also increased, as has our sensitivity and the accuracy that we can study the night sky with. And if we go a bit more deeper into the wavelength regime, we can see that.
Sorry, Hanno, it's still there. That grey square. It came back. It temporarily went away, but when you went to the full mode, it came back.
I just need to stop, see if I can fix that, because I'm specifically sharing only the one screen.
If you can minimize the window, it doesn't show on your computer. It will not show to us either.
It's already closed.
Oh.
This only happens when I go into slideshow.
Indeed.
And then you have to excuse the click to add more text on this thing.
No, actually, it appeared again in our screen. Great. Yes. Thank you. It's gone. It's really small now. It's good.
I know what it is then.
Great.
There you go. See if that. Hopefully it's gone now. Seems what's happening is when I go into full screen mode, everybody on the Zoom chat goes into the middle of my screen. Right. So in the wavelength regime, we can see that the optical surveys has so far cataloged the most new sources, and with LSST that will definitely increase to fainter sources. And since we are also looking in the time domain, and discovering new transient sources, it becomes paramount for us to classify those sources before they have finished so that we can do follow-ups with other observatories like here in South Africa with the SAO observatory. On top of that, as our information has increased, we also increased the storage space that we need to store that information. And the LSST is expected to store more than 100 terabytes of data. And it is impossible for any one person or any group of persons to go through this data by hand. And even with today's algorithms to go through this, with this amount of data, those algorithms will start falling short. And to that then, I started looking at machine learning classifiers to see if we can reduce the amount of footwork that we as observers need to do to find new transients and classify them. And one of the classifiers that I looked at is one of the simplest. It is the decision tree. And a decision tree basically looks at a feature and then splits it based on some binary decision. Is it brighter than a certain threshold, or is it fainter than this? And then passes that through to one of two branches, which then looks at another feature and does a splitting again. This splitting happens until there is no more, until at the end of the branch, there's either only one object or one object class. But a decision tree is very, very inaccurate and is very, very prone to errors. So what we do is we use a bunch of decision trees, thousands or millions of them, and combine them into what is called a random forest, which is a type of bagging classifier. And it looks at the average classification of every single decision tree in the forest. And that then is able to throw out any anomalous classifications that only one tree finds, and thus increases the total accuracy of the classification. And this classification for random forests can go up to 95% for light curve data of transient events. But unfortunately, you need the entire light curve to classify efficiently, because the more data you have in a light curve, the better features you can extract and the more features that you can extract. And this obviously will not work if we're trying to promptly classify transient events. So next, I looked into neural networks, which takes inspiration from the brain and is very good at pattern recognition. And in essence, it takes some input, passes it through an activation function with a weight of each activation function, and then outputs that into the next neuron, which then does the same. It passes the new input through a weighting function, an activation function, and then passes it over to the next one until it reaches the end of the network. The good thing about neural networks is with very little data, you can classify a transient, any sort of class that you apply to it, as long as you have enough data to train it on. And one of the things that they've done with this is use Raman spectroscopy to try and classify molecular structures and molecules. And they've gotten this process up to about 92% accuracy in classifying molecules. But for me, I'm interested in finding out if we can classify our light curves with less than 5 days of observations. And we have a few approaches for this. One of them is to use what we call a convolutional neural network. Yeah. It's to use what we call a convolutional neural network, which passes a little convolution matrix across your data, and then constructs another set of a feature space that is smaller than the original one. But again, for this one, it only works based on images or video inputs, and won't really do it for one or small dimensional light curve space. So I then pass that on to another neural network, which I will talk about a little bit later. And I'm going to mostly skip the slides I have for the LSST, since we all know what it's doing. But most importantly, with the 3.2 gigapixel CCD and the 37 billion stars and galaxies we will be able to survey, and the 10 million alerts a night, it is impossible for researchers to go through this data every night to see if we find any new transient events and trying to classify them. And for this, a machine learning algorithm works really, really well. And neural networks is able to take that 10 million new alerts a night, and even on a average laptop, it is able to then classify these transients or do classification or regression on these transients in less than 10 minutes, allowing us then to use those classifications and do our own cuts on the science data to see what we are interested in, and then decide which sources to follow up on. So to classify transients, I used the photometric LSST astronomical time series classification challenge, quite a mouthful, or the plastic challenge. That was a challenge that was hosted on Kaggle to see if we can classify transient events. Now, in the plastic data set that we got on Kaggle, they had 19 transient classes and about 8,000 light curves in the training set. But this data set was constructed using the older LSST cadences, and so we had very little feature space to work with. The new data set that I created, I used the newer LSST cadences, but used the plastic models that they used to construct their database. And this light curve that I'm showing you for supernovae 1 is basically what we receive from the model itself. At every single time step, we have data in every filter. And what we now need to do is we need to see if we can interpolate this light curve into a new data set at the LSST cadences. And for this, then I constructed a new data set with 12,000 training light curves, validation light curves, and testing light curves. And once this data set is constructed, we get a light curve that looks sort of like this. And for this light curve, we do not have observations in every single filter at every single time step. As the data is coming in from LSST at the filter that they did their pointing in, we receive the data and immediately plug that into the neural network with all the rest of the data until we get a light curve. And to do this, then I decided to use Gaussian processing to interpolate the data. Now, we get a few interpolation methods, and the most common is linear and quadratic interpolation. These two fall short though, because they were designed to do it in univariate data sets where you only have a single dimension. Gaussian processes is able to take this a step further and do an interpolation across not one-dimensional space or two-dimensional space, but higher dimensional spaces. And in this 3D plot I show, this is what a interpolated light or the actual light curve looks like when we plot it as a surface. A Gaussian process is able to fit the surface, and we are then able to sample any point on the surface to apply to our light curve. And crucially, that means if we, for instance, change the redshift, we do not have to do a linear interpolation between two adjacent data points in different filters, but we can then use the Gaussian processor to sample a smooth point between two filters wherever we need it, and at whatever time step that we need. So I settled on the Gaussian processes. Unfortunately, it is not a fast process. If you want to do just a simple connected dots, then a linear and quadratic interpolation works a lot better. Even for a simple Gaussian process with a few thousand data points, it can take minutes to actually get the surface plot for us to sample. But it works really well if we only have to do it once and then sample say 1,000 different light curves from this one surface. Then it works a little bit better than linear and quadratic algorithms. So the database was constructed in this way. So we used the plastic models and then separated those models into our three training, validation, and testing sets. Each one of those sets then was used to generate a new LSST pointing using that Gaussian processes. And we then shifted them. So we simulated them at their rest redshift, and we then sampled them at those filters that corresponds to our observation frame. So we sampled them between the filters at different redshifts and at different starting times, and then constructed our model, adding some noise, changing the redshift, just basically dirtying up the models a little bit, so that we don't get perfect data. These training models, each model then is independent of the previous one. So we don't use model 1 and then split that into the training, validation, and testing sets. We use model 1 in the training set and model 2 in the validation set, for instance, so that they can be seen as independent sets. What I also do then is I lose the data set within, or a light curve within the data set. I just throw it into the trainings data set, and then I lose it. It has a random name attached to it, and only in the metadata do we know what class it is. So that we don't later on can go and say, let's just train on 1 or 2 of the models that, or the light curves that actually look good, or that we know about. So I settled on using a recurrent neural network, which is a network that looks at features that is only viable in the forward direction. A recurrent neural network is most often used if you want to track subjects in a CCTV video footage, for instance. But what makes this very nice, very cool for us, is that when we apply it to light curves and we give it only 10 data, or say 100 data points, every neuron in the network is only able to see data points from previous observations. So on day 10, if we look at the data, the network is only able to look at the features from the previous 9 days. It does not see the future events, and this allows us then to only use the past events to try and classify our transient sources. So once you have run it, and you need to you get quite a bit of information. Every light curve has a probability of belonging to a certain class. But if you have 100,000 light curves to look through, it is not really really efficient to look at every single one of them. So what we do is we can construct a confusion matrix that classifies how many of this of a certain class with a label that is that we know is the true label was actually correctly predicted. So the confusion matrix then looks at the ground truth versus the predicted label that we give it, and with this one graph, we are able to do quite a bit of statistics. One of them is the precision statistic, where we take the true positive events, i.e. the events on the diagonal that we know is the true events, and compare them to what all the other events or classifications results are. This and the same with the recall. We do the same with the true positives, but now we look only at the columns versus the rows. And these two statistics tells us then how accurately our model is able to predict a bunch of light curves. And for most of this work, I will focus now on the confusion matrix. However, we must note that on the confusion matrix was designed to work with an entire data set that we give it, not the way that I did it, which is going to be in the next few slides. So, since we can use the neural network or the recurrent neural network, we can now extract our classification at different epochs from our light curves. And on this one, we can see that on the first 5 days of observation, after we received our trigger, the network does not really perform very well. Supernovae 1, all the classes are less than mostly 50%, except for the 1As, and the AGN classes, which are quite distinct in their light curves. After 15 days, we can see that our network has now very efficiently split our sources from the non-galactic sources to the galactic sources. And so even though at this stage it doesn't really do very good classification for what we want to do, we are able to say that this transient is an extragalactic transient like a supernovae, and we can then put our light curve into a more dedicated classifier that was designed to classify, say for instance, only supernovae. But we aren't really interested in that. We are interested in classifying as many of the transients as we possibly can. And on this bigger confusion matrix, we can see that from the supernovae classes, we have about 5 of them, and a tidal disruption event, some AGN, and then only 2 galactic transient classes that we have. And then in a last class, we have an anomaly class, and this will become important in the next few slides. And this is what I then for the last few months focused on, is trying to figure out how can we get an anomaly score out of our classification. Because if we only classify events that we know about, the network, if we give it a new transient, it will try to put it into one of the classes that we already know about, which is not really what we want to do. On 30 days, we can see that we have very good classification, and this is more or less what traditional machine learning algorithms will give you. It will give you a classification of about 60–70% on the supernovae classes. If we have more than one, if you only look at supernovae 1 versus any other supernovae, the classification becomes a little bit better. But crucially, on our galactic classes, we get more than 80% accuracy on some of our light curves. And for the anomaly detection, since we have this extra class, and this extra class we did not add any data to. When we trained, we just added an empty class of no light curves in it and immediately froze it so that the network does not train on it. So what the network then does is, once we give it our testing data set, what is going to happen is it will try to classify it as all of the classes, including the anomaly class. But since it already knows what the other classes looks like, so in this case the supernovae 1a, we get a very good classification after only about 10 days of observation. And this big bold black line at the bottom is then our anomaly class. So this light curve looks like any standard supernovae 1a. Same for the one on the right. We can get this one is classified, predicted as a supernovae 1a as well. And you can see within 20 days we get our prediction. It is just slightly after the peak. But for the next one, where we have a supernovae 2, this light curve is not very well sampled. So the network struggles to classify it. And because it's struggling to classify it, it adds more probability scores into the anomaly class. So our anomaly class increases, and we can then use this anomaly class to actually get a probability of this being an anomalous object. And in this case, it is a 30% anomaly score. So we have about 30% confidence that this is an anomalous object. One on the right, we start off, and then the network sees that this does not fit into anything, so it assigns it a small anomaly score. But then the data point right after it constrains the classification, so the anomaly score then goes down, and we immediately get a supernovae 2 classification. The idea then is to use this anomaly score to find new transient events that we have either not seen before, or might be in highly obscured regions of the sky, or might be a transient that we do know about, but behaves slightly differently than what we would expect. The same happens for our galactic transients, so the Marais classes and the IR classes. We do not have a lot of data points for them, and they are quite noisy on the timescales and the cadence from LSST. So we will mostly get some noise, but we will also get an anomaly score with that, and we can use this then in relation to what the other scores, probability scores are. In this case, eclipsing binary and an AGN score, to see that this is an anomalous object that is being muddled with other classifications. So we might then look into this. And in conclusion, for this project, we try to find new ways of analyzing data using or transients using machine learning processes. And while random forests provide very high accuracy, it requires complete light curves. So we can't really use it to include anomalous classifications in our observations. So, but using neural networks, even though they require very large data sets and is highly adaptable, we can fit very, very complex models to it. And the more data we supply the neural network, the better its classification results will become, and the less likely it is to apply an anomalous class to any of our data sets. And LSST will bring a new era in transient astronomy, and by mapping the entire southern sky, we will get millions of alerts a night that we can then use to see if we can constrain our models of these transient events. And with the network that I'm designing, with on average more than 80% accuracy on the plastic simulations, we will be able to very, very quickly try and classify these events so that we can then do follow-up observations. And specifically, here in South Africa, we want to use the South African Astronomical Observatory to do these follow-ups with our large telescopes. And for my data set, I have 9 known classes, mostly including supernova events, since they are the most numerous classes in many data sets, and 1 anomaly class. Now, the anomaly class consists of data of light curves that we and sources that we have either never seen before, like for instance a double microlensing event, or classes that are very, very rare, like kilonova events. And in my case, I just added a few of them. I did not go into detail on these in this talk, but the anomaly class allows us to then classify anything that we have very, very little data about, so that we can further investigate them. My network is able to classify events with up to a probability of about 60% within 1 week of observations with LSST, and that is about 3 pointings in many of the filters. And it also calculates an anomaly score, so that we can see if we can do follow-up observations on these anomalous classifications. And although there is early light curve confusion in the classes, this is not necessarily a bad thing, because we are very quickly able to separate out extragalactic transient events from galactic transient events, so that we can do more targeted classifications. And thank you.
Thank you for that excellent talk, Hanno. And congratulations on the system that you've developed. I think that's an extremely powerful system, clearly. And there's been a lot of questions in the chat already. So if we shall, starting off with the question from Martin Mackler. Martin, do you want to repeat it out loud?
Okay. Yes, thanks for your talk. Very nice. So there's this data set called Elastic, which is kind of plastic, but also produced with so yeah. So you have this method using Gaussian processes, and you generate new data from plastic. How at the end does your new plastic differ from Elastic?
I haven't looked at Elastic data yet. The idea at the end is to use this network without retraining it and applying it on the Elastic data to see what we get.
Okay.
But since Elastic adds more metadata to it, to the light curves, we can extract that metadata and add that into the network, which will increase the classification. But if you want to do that, then I need to simulate that metadata as well. So at the moment we haven't tested it on Elastic yet.
Thank you. And is this new Elastic data available, or the method to generate it?
I am not sure about that. Or someone who's actually involved with the Elastic simulations.
Sorry, I meant your new plastic. Sorry, plastic.
Yeah, at the moment it's just saved on a cluster.
Okay.
Yeah, and it will be made available once I'm confident it works properly.
Thank you.
Thanks, Martin. And David.
Yes, I was just wondering, I think, we all realize that the plastic, I'm not sure about the Elastic, but the plastic data is somewhat top heavy with supernovae or extragalactic transients for good reason, because it was, I guess, dark energy survey people who produced this. And you do have a couple of different classes of galactic transients, but for those of us who only work in the galaxy, we sort of think there is a somewhat underrepresentation of other classes of galactic transients, like, for example, things I work on, CVs, X-ray binaries. Do you have any plan afoot to sort of extend this to include better representation from galactic transients?
There is a plan for that. So we have a small telescope in South Africa called Meerlig, which is doing a small mini survey of the entire sky, and they are picking up quite a few galactic sources. Once we have solved some of the pipeline issues for the reductions, I plan to use those light curves and do the same type of simulation with the Gaussian processes to include some more classes to my database. We also have, of course, the ZTF database, but ZTF, since 90% of the observations are in the GNR filters, it does make it a little bit difficult to extrapolate to the other filters. So we do have access to that data and some of the galactic sources, but it is, since it's just observed in the GNR, we can't really extrapolate properly to for instance, the Z filter. So it makes it a bit difficult to use that in this data set.
So you're saying that the Meerlig data in that regard is superior because it's basically all of the Sloan filters, even despite the fact that it's only typically got so far sort of 5 pointings per field, if I'm not mistaken.
Yes. So the 5 pointings per field is mostly in the extragalactic and the outside of the galactic bulge. We do have a deeper survey in the galactic plane itself, which most of those, and of course the globular clusters and some open clusters. So the galactic plane survey, most of the sources have about 50 data points at the moment. We go visit them once every 5 days or so.
And I guess other surveys like, for example, Assassin or Atlas, because they're only 1 or 2 filters, the same remarks that you made about ZTF apply.
Yes. I do have to mention that there is 3 small telescopes currently under commissioning that is related to the Meerlig telescope, the Black Gem telescopes, and it's three telescopes sitting right next to each other, which will each observe a separate portion of the sky every night, or a third of the sky. And if that data, if I can get my hands on that data once the commissioning is finished, we will have a data set comparable to what ZTF is currently have, but in all of the Sloan filters.
Have you considered looking at some of the others, like the VBV survey? Is that any use to you?
I don't have access to that. And I can see if I can contact the PI and see if I can get some.
Yeah, it was an ESO survey, so I think eventually those data then have to go public, but I'm not certain. So it's worth checking into.
Yeah, but I have to look at the fact that, so for instance, the ZTF, while they do make all of the data available, they do not put any classifications on the data. It is just the raw data that they give us, and that makes it extremely difficult to actually go find enough sources. And we have to use other methods to then try and cluster them together, and it makes it difficult. So if there's a database out there that has the classifications with a source for the light curves that I can go extract the light curves from, I would definitely use that.
Well, we should definitely talk, because at LCO we have data from a previous key project which was in the Sloan filters for galactic bulge fields, which was in 3 filters, and we have the entire light curve data set, which I am busy trying to produce and cross-match against known variability catalogs.
And that'll be really useful.
When that's ready, in my copious free time, we should talk, because it sounds like it would be really useful to you.
Yes.
If I could pick up on that, and taking the chair's prerogative to switch in my own question. I know the goal here is particularly focusing on transients and the need to rapidly identify things like supernovae at early times. But after a few years of operation of LSST, we should have built up a catalogue of sort of known variable sources, including some known outbursters, which should be excluded from all of these processes in advance, because they're just a source of confusion you can remove. What I have not heard from any of the broker operators or anyone else is, where are we going to have that centralized catalogue of identified variables? You know, we're going to have the LSST light curve data catalog in the Rubin Science platform, but I don't know about the second order products of identified variability catalogs. And I think, sorry, go on.
What's it, the variable stars, general variable star catalog, I think it's called. There is that, but that is a few years behind, and they only include sources that have articles, peer-reviewed articles,
where they've classified it. The GCVS, Russian,
right,
one.
I think
the only one I know about that has it.
Yeah, and I think for LSST we're going to need something on a much bigger scale.
Yes.
I mean, would this be something that would be hosted like on Vizier, or I don't know, some of the other?
It could be. I'm thinking in the first instance, for the Rubin community, it would make sense for it to be hosted on the IDACs in the data access centers, so that you know, when you're running systems like your classifier, you can just call on this catalog as a pre-filter, and then go ahead and classify everything else that you haven't already classified. But there needs to be that sort of memory in the system as we go through the survey. And I think that infrastructure has yet to be built. And I think it's something that maybe TVS should really think about.
Actually, I'm thinking, how are you going to include, or are you going to include follow-up observations for some of objects in a big scheme?
That's a great question, Darko. Hanno, do you want to jump in there?
Oh, I didn't catch that. I have no plans to host such a or even attempt to do this sort of database setup for variables, because that is going to be a full-time job. Just keeping up with that.
And as Hanno's co-supervisor, he has a PhD to finish this year. So
yes,
right. I think it does speak to a wider question of how are we going to coordinate follow-up for such an enormous category of data sets, and so far it's on the community to kind of self-organize.
Point is that follow-ups are not going to be too many of them. Let's put it that way. So it is fairly easy. You do not expect too many points or too many objects to be follow-up.
That's fair. That's fair.
So if I can jump in, the ZTF is actually having a meeting on Friday about small telescope follow-ups in general of ultimately LSST. But I think this is something that really I do agree TVS should organize. We actually do this in a subset of ZTF right now. We have a spreadsheet of objects that are highest priority for follow-up. And so this is what I hope we can organize the people that do want to do follow-ups. It can be done within a small category. It'd be easiest to do it within CVs, for example, because we know it's a small group of people, but it can be done on a more general basis by category of object, where the people have a sheet of what comes through the machine learning classifier as people think as important for follow-up, and those go into a spreadsheet. And the spreadsheet that we have is active so that people that have done observations of a source then put their date in there and their name of which telescope it was done on. So there's not repetition of everybody doing the same sources. So you can, when you have an observing run, you just bring up this sheet and you look at what the highest priority is and what has been done already. And it's extremely useful. And I hope that something like this can be organized for LSST, because it's what we're going to have to need, really.
Yeah, and I am aware of various different groups who are organizing. And it seems like there's a number of parallel efforts going on. In fact, we have a workshop here at LCO right now organizing a follow-up for gravitational wave, a supernovae and other transients, and a target and observation manager system to handle what you described as the spreadsheet coordination aspect of it. The same things happening in microlensing, but I think at the moment it's individual communities are getting together, and I think we need to do more of that in more of the subgroups.
That's right. I mean, I think, and there could be an overall umbrella of TVS. And so people that are interested in the various subgroups can then just go first to this main page and then find out what group, they can look at, especially the people that are interested in more than one group, it's.
Yeah. And
overlap.
Yes, that's something we should talk about, I think, perhaps in a different brainstorming session. I'm conscious that there are a number of other questions to get to, but you've raised a very good point. Thank you, Paula. Samaya, you had a question.
Yes, thank you so much for the talk. Very interesting results. I wanted to ask about the Gaussian processes, using Gaussian processes to interpolate. How did you verify the interpolations? Like, how did you make sure that they do not overfit?
Yeah, so Gaussian processes return an error on their fit. So it's related to Bayesian processes. So you need priors and error bars and errors to fit. So it gives you a confidence of not only how good the fit is, but in the areas that that there's no data, it returns an error. And if the errors get too large or too small, you can then throw the data away, because then it has obviously underfitted and overfitted on some sources. So I do check if the errors that each interpolated data point returns is too small. On average for the entire light curve, it might have overfit and missed something. The same if it's too large, then I throw it away because it has obviously not fit the light curve properly.
Thank you. And can I ask a follow-up question on that?
Yes.
Do you have like a single kernel to fit, or like do you adjust a kernel based on like what type of light curves you're fitting?
Yeah. So I'm fitting on a Matten 3.2 kernel. So for Gaussian processes, the kernels don't really influence what is being fit. The kernels is just used to set up a covariance matrix for the data. so that your your last data point does not influence your first data point in the fit. So if you're working in the first data point, you use the correct kernel, then say the fifth data point will have a minimum effect on what the fit is. So if we can find a kernel that works mostly for all the sources, it will work well enough for all the sources to fit, but not overfit.
Okay, great. Thank you.
Yeah.
And returning to David Buckley, you had a question about the classifications improving with time. You're muted.
Sorry, I was muted. Yeah. I mean, obviously, you were showing that things improved radically, like over even 5 days or 10 days. But
yeah,
is there a sort of I mean, I'm imagining that there's I suppose it depends exactly on the class of object as well. But is there a sort of time scale you'd say after so many days, the confidence of classification is X% for this class of objects? Are you going to sort of arrive at that point in your simulations?
Yeah, so it doesn't really work like that. So the confusion matrix that I showed is so you take the highest probability of it being one class, and then set it to be that class in the predicted label. So what it is showing is the class that it has the highest confidence in. And as we have more data points, even though the accuracy increases, what the confusion matrix shows is how many % of them is the predicted class has the highest confidence in. So as we are increasing every pointing that we do and add more data to a light curve, we don't increase the accuracy of the entire network, just the confidence we have in a single light curve.
Presumably that must be a function of the survey strategy in particular, because I'm thinking of some of the survey strategy simulations that have been done where they have deliberately altered the survey strategy to do repeated visits within a night in different colors in order to more accurately classify fast transients. Do you have a plan to take a look at some of those simulations and see if they would perform any better?
That's going to be some of the new options.
Yes, some of the V2, 2.0 and 2.1.
I haven't resimulated it for that yet, but this one is done on the 1.7 rolling cadence.
Right.
So it is mostly similar to what the new ones. And so in those two, in that same day, there are some data points where we have two filter observations, and the network notices that and then calculates a color and tries to apply that to the classification.
And do you see a noticeable improvement in the speed of classification?
Yeah. So in the galactic sources, we do get that when we add more filters in the night. When we do return visits, we get much better jumps in confidence.
It'd be interesting to see what the trade-offs are between rapidly classifying something versus actually scanning more of the sky, but perhaps that's a wider discussion.
Yes.
I see one more question from Lukasz Steinwinder.
Yes, thanks for the very nice talk. I'm still not quite understanding how you are like putting samples into the anomaly class, because you don't have labels for the anomaly class, right?
No,
it's just
so during training, while we do have a anomaly class, there's no data in it. We just add a new extra label and then freeze that label so it doesn't try to train on it. So that label is just open. So when we same for the validation, there's no anomaly data on light curves in the validation set. The anomaly on light curves is only in the testing set, and the testing set does not have any labels, and that we can use to better the fit. They do have labels so that we can make sure that we fit correct, that we classify correctly. That's how I know we have anomalies. When it tries to give a confidence that this one light curve belongs in the anomaly, and I can see that it is a kilonova, which is just never seen before.
Okay, but the thing I don't understand then is how the essentially, why does the neural network then not learn essentially to ignore this anomaly class completely, because it never comes up? That's something that's...
Yeah. It's because we froze it. We froze the training. So it starts with the parameters that we initialize it with. And it is the 12th class. So it has about 8%, 8% of. So if we, for instance, just immediately tested it on without training it, 8% of every light curve will get thrown into the anomaly. But as the network trains, it learns from what the other classes look like. So anything that does not look like the other classes gets thrown into the anomaly class.
Okay, so you initialize the anomaly essentially. So you start with the anomaly and then try to pick out the samples from there.
Yeah. And not fit it at all. We just ignore it. It's there, but we don't look at it.
Okay, yeah, makes sense. Thanks.
Yeah.
Okay, and one last comment from Paula about the CV catalog from ZTF.
Oh, no, that was just when you were talking about having catalogs of information available so that you could just use them. There is, Jan van Rustel is putting together a CV catalog, which hopefully will be published in the next year, at least the next few months.
Excellent. What limiting magnitude does that go down to? Sorry, David.
It's all right.
That will be 21st, I think.
Okay.
It's mainly based on the alert on the difference imaging, not the more robust PDF.
Sure, that would make sense for the time domain, the colors. Yeah. Oh, thank you. Well, that's great news, Paula. Thanks. Sorry, David, go ahead.
No, I was just going to say in relation to the ZTF CVs that maybe Hanno, you can just mention that you are looking at what 600 odd light curves in the hope to well, for this survey paper / cadence paper on CVs.
Yes. Yeah, so I am using that about 600 of the CVs from ZTF to test them on some metrics I designed. So we can see how many of them we can actually detect over the course of the 10-year survey, and where we might need to shuffle around some observations. Because currently for CVs and for many galactic sources, we do want more blue observations, but that is obviously lacking. So we need to see how many of them we can actually classify if we have those blue observations versus if we don't.
When you say blue, do you mean G or U?
U and G, yeah.
Yeah.
Okay, thanks everybody. Are there any final questions for Hanno?
Actually, I might have some silly one. In a sense, as we are playing with the Rubin in 6 filters, how do you compress them into single light curve so that you have a higher cadence?
So if we have the entire light curve, then we can use the Gaussian processors to do this. So we can fit the entire light curve as a surface, and then only sample in one filter, once every day, once every 2 days. That's what I did with one of my initial databases when I was testing out the neural networks. I had simulated observations in every filter once every 2 days. But this network is a little bit more realistic. But Gaussian processors allows us to do this, to only sample what we need. So if we need observations in just a G filter, if we fit the entire light curve, we can sample at the G filter, whatever we need.
Okay, well, thank you all for your questions. So we're coming up to the hour now, and I know everyone has commitments, so we will wrap it up there. And Hanno, thank you so much for a really fascinating talk. That's a fantastic project that you have there. I assume you'll be writing up for your thesis very soon.
That is the plan, but everything things keep getting in the way.
Well, good
Always
luck
more
with
to-
your thesis.
Yeah, always more to do.
I'm sure there is, but you have an
Yeah.
excellent body of work there. I'm sure it won't be any trouble.
Thank you.
Thank you very much for your time in the talk.
It was a pleasure.
And thank you all again. I will see you next time.